Hi everyone, welcome back to episode 3 of the AI co-learning program. I'm Bruce. I'm happy to continue this journey with you all. So today we're honored to have Professor Michael Mahoney to be our guest. He'll be delivering a talk on the foundations of scientific machine learning. So Professor Mahoney is a distinguished professor in the development of statistics at UC Berkeley. He also leads the machine learning and analytics group at Lawrence National Laboratory. And also, he is an Amazon scholar. So, Professor, thank you for joining us. We've been looking forward to learning from your research and insights. So, the floor is all yours.
All right, well, thank you. And thanks for the invitation. I'm glad to be here. I think someone needs to share the screen back with me because I don't think I can access it. There I go. And good. All right. So, as I said, thanks for the invitation. I'm very glad to be here. And I guess good morning. I'm actually in Europe on European time zone. So I guess people are all over the place. And
Yeah,
like usual for this sort of presentation, I can't see you. So either, depending on the number of people, either interrupt or holler or post questions, and I guess um, Bruce, feel free to interrupt and ask as appropriate.
sure.
What I thought I'd talk about today is something, and that will touch, I think, a lot of things, but I want to parse the title first. The title is Foundational Methods for Foundation Models for Scientific Machine Learning. So foundation model is sort of a term of art in a sense, but it's also a term of art that's been widely misused. Well, I don't know if it's misused. It's been misused, but then also used for a range of other things. And so roughly it was coined to describe things like ChatGPT that are really a foundation on which you may build stuff, those sorts of models. But the question might be how broad is that idea? And I'll say what exactly that idea means in the original characterization and then how other people use the term. And then the question is, could you do something similar? I mean, ChatGPT, as you know, and vision models and other related things are really taking the world by storm and leading to sort of lots of changes in the landscape. Could you do something similar for scientific machine learning? And by scientific, think broadly, science or engineering. I don't mean software engineering, but civil or electrical or mechanical or anything. Stuff that is sort of traditional science or engineering. And I think this is of relevance partly on an industrial side. I mean, big industries that are not necessarily the big tech companies are interested in various sorts of engineering applications and pipelines. It's also of interest at universities, right? A lot of universities train students, and the students may, if they do CS, whatever, go off and work at a tech company. But a lot of departments, train students, and the students go and work in various scientific or engineering companies. You might have a degree in chemistry and work at whatever, Pfizer, Genentech, or you might work with Shell Oil or something. And so, can you apply similar principles to these sort of things? And I think it's of interest more broadly because certainly you see big wins in the scientific machine learning space. Nobel Prizes were given out last year, just as one example, in say chemistry, in physics too, but that was a little bit different. And so some people think that's a big application of AI and ML techniques. And how would you do that more broadly? Because those aren't the main forcing functions if you go to machine learning venues. The main forcing functions are language or images or other things like this. And one of the things you'll see that I want to emphasize is that you really need to think through what I'm calling here foundational methods. So what are the basic methods, right? If machine learning tends to select for areas where you're more domain ignorant and have a lot of data, maybe internet ads or social media, but language or images, you get certain types of techniques, stochastic gradient optimization, and a range of other things. And then if you have a lot of compute, there's a lot of things you don't have to be particularly careful about. Properties of Hessians, which are second derivatives, or hard constraints, which might matter in certain physical applications, or temporal properties and whether you violate causality in certain temporal predictions. But in other engineering applications, that might matter a lot more. So if you shift the balance to applying the ML methods to domains where You still have a lot of data, but you know a little bit more. If those aren't sort of the main thing the machine learning community thinks about, those foundational methods are going to be lost. And so this is basically the topic I want to address here. Can you get foundation type models for science and engineering applications, the sort of thing universities do all the time? And what are foundational techniques, applied math techniques, or techniques that would have to address? So that's sort of the title, parsing the title. All right, so I'm just moved to the next slide. If you don't see that, let me know. And I'm calling this physics-informed learning. So I'm using physics, and by that, chemistry and biology and engineering. I don't want to be too narrow in what I mean by that. And the main point here is that if you do computational X, where X is physics or chemistry or civil engineering or material science or whatever, computational science is an interesting area because in some senses, it's a tool to incorporate physical insight. If you have more domain knowledge, what that might mean is I instantiate it as equations, partial differential equations, or invariances, or something that I know about geospatial or spatiotemporal properties. But as I was saying, until recently, it was missing from mainstream ML in a lot of ways. And so computational science is sort of interesting because it really can look into the future in a very different way than machine learning. Machine learning is a very static thing, right? It does classification and regression, but it doesn't really think very much about time. And even if you look at statistics at a time series analysis book, there's a whole bunch of t's there. So clearly there's a time variable. But if you ask, where really is the time? Or if I know a lot of least squares and linear models and other things like this, what more is there besides adding an autocorrelation that's along a one-dimensional temporal axis? And in general, there's not much. In machine learning and statistics, computational science, they frame things in terms of differential equations. It might be a molecular dynamics, it might be a transport equation, and you can really look into the future. And so it's sort of remarkable if you think about it, right? Someone has worked out and knows, 8,000 years from now that there'll be an eclipse on a given day going over this path of the Earth, and it knows that to within, a minute or something. I mean, that's incredible if you think about it, right? I mean, looking at 8,000 years ahead, and you can know that over, Berkeley or wherever, there's going to be an eclipse from, this time until 17 minutes later. And so you can't get that precision looking forward everywhere, right? But I mean, the fact that you can do that anywhere is actually sort of remarkable. So you can really look into the future. That's an area where you have very strong control on the equations and sort of nothing else. So you run the celestial mechanics for it. But there's a wide range of areas where that's like that. And so the question is, can you look into the future in an analogous way? And you really can't do that currently in machine learning. And so basically, when I come back to a theme of spatiotemporal, how ignorant can you be about your engineering or scientific use case and still do something useful? And one very common theme is that scientific data are in 2 or 3 dimensions, and they evolve in time. And so we'll return to that sort of as a very, very coarse prior. And when I say coarse prior, I mean, what if you know nothing about computer vision and you want to classify cats and dogs? You might know that an image is a 2-dimensional thing, so maybe you should do convolutions to smooth out local information, right? And you do that in a whole bunch of other things, and you can get great results. And what do you know about language? You know that, at least in English, subjects are before verbs and adjectives modify, and there's a certain sentence structure. And so, there's a sort of linear, call it temporal, but linear ordering. And so how little can you cook into the scientific knowledge and still get something like looking into the future? That's sort of what we want to address. All right. So there was a phrase that I saw, I don't know, 5 years ago or something. And I didn't really talk about it much because it was one of these things that was, I mean, you either knew it or you didn't. But I've heard it on several different occasions within the last 6 or 8 months from scientists, so relevant to the title of the talk here, from scientists, card-carrying scientists who are sort of doing, dabbling in the machine learning space and seeing what's happening. And they both said basically, geez, what's going on with this bitter lesson? The machine learning people are going to come and gobble up our lunch and take everything from us. So if you don't know what the bitter lesson is, I'll walk you through it. And even if you do, I'll walk you through it because it's a little bit subtle. Sometimes it's mischaracterized, but I think it's a leading order thing in this discussion. So this was a term coined by Sutton, I guess. I think it was in 6 or 7 years ago. And basically his claim was general methods at level computation are ultimately the most effective by a large margin. You might say, yeah, obviously, but what's the alternative? The alternative is to cook in your insight, your narrowed provincial insight that you happen to get in 2025 based on 10 or 20 or some number of years of experience that you think will port to something much broader, right? Which is what people usually want to do, right? They want to cook domain insight because they say I'm an expert because I've been studying this for years. Most AI research, and this is not even about science, this is about ML and AI. So this is a statement on the last 70 years of AI. Most AI research has been conducted sort of as if the computation available to the agent, to the person or the machine or whatever, were constant. Right now there's a certain amount of computation. Depending on the number of dollars you have, you can get a small, a medium, or large machine, but it's sort of fixed. I mean, as opposed to varying by a factor of 10 every 3 years, whatever it is, for the last 30 years. So when the amount of computation is constant, if I want to beat you because I want to get to market first, or I want to get a product out first, I want to get a paper in, there's an obvious way to do it, and the obvious way is to cook some insight that I have into it. I say, geez, I know that not only are images two-dimensional, but they usually are centered and faces are registered upward rather than sideways, and so I'll take advantage of that and I'll design features around that. So if the amount of computation is constant, using human knowledge is basically the way to get improvement. Doing that, the third bullet, seeking an improvement makes a difference in the short term. And for that, researchers seek to leverage their human knowledge of the domain. The only thing that matters in the long run is leveraging computation, designing models and architectures and structures that are forward compatible with 10 or 100 or 1,000x more compute and more data. So don't spend time thinking about what you know, because it was designed with a particular size scale in mind. Think about how to design models that can absorb more data and more compute. Now, this is always bad advice to follow if you want to get a product in production next quarter, or if you want to get a paper in at the next review deadline, because then sprinkling with a bit of domain knowledge, you can highlight the novelty and how something's different. And sometimes that's good if you want to be first to market to get your paper in. But if you want to build something in terms of sustainable sort of theoretical infrastructure for the long term, it's a bad idea to do that, right? You should focus on the long term. So these two things need not run counter to each other, but in practice they do. You spend an hour or a day or a week or a month on one thing, you're not spending it on another. And if you made a big psychological commitment because now you're an expert in domain X, you don't want to think about ignoring all that insight and focusing on computation more generally. And the human knowledge approach tends to be a little provincial and to complicate methods and make them less able to take advantage of 10 or 100 or 1,000x compute. So building in how we think, a lot of people want to motivate machines by how people think, just doesn't work in the long run. And there's a lot of examples of this. Think of speech recognition. DARPA was funding stuff in the 70s. Roll the clock, that are heavily engineered based on the structure of speech. Roll the clock forward. Don't need that. Image analysis. You can do lots of fine scale features, and depending on roll the clock forward. Don't need that. Computer chess. Do a decision tree and cook in domain insight about experts and test all the opening strategies. Roll the clock forward. Don't need that. And so now you're in science. And you say, geez, I need my scientific insight. I need equivariance. I need some spatial. I need to cook in the laws of physics. I need to do this. We're in the middle of that. Roll the clock forward and prediction. You're not going to need that, right? So you should build general structures. Now, the inductive bias, so this does not say, to be clear, this does not say know absolutely nothing about the domain and be completely ignorant. Because even for image analysis, you cook in convolutions, right? And so then it turns out transformers, which allow you to do certain types of training on sequential structures, it's not as good for inference, but allows you to do certain types of training for sequential structures, is good for language. And it's not particularly good for images, actually. But then it turns out if you take the images and jam them into the form factor of discrete tokens, do pre-processing to make them talk to that structure, then you can get image transformers and vision transformers and stuff. And so you want to feed the data to certain models that are forward compatible. So you don't want to know zero about the data, but in a sense, you want to build models that are forward compatible with the scaling and maybe cook domain insight in as weak a way as possible or as little as possible. So the answer is don't be completely ignorant, but cook it in as a very second-class citizen. All right. So this is a bit of a preamble, but now what is a foundation model? And I gave you an example, but let me talk a little bit about that. And the question is, can you hope to train a foundation model for scientific ML? And then a bunch of stuff, and I'm not going to have time to get through all of this. These slides are actually on my webpage if you're interested. And the second half there's a bunch of foundational questions, and a little bit more technical. I can give you an example of one or two. Implementations, how do you actually implement the stuff on hardware? Some applications and looking forward. So I'll spend most of the time on the beginning, but there's a broader picture if you're interested in any of this stuff in more detail. So what's this term foundation model? So it's think of it as general purpose, for lack of a better term, technologies that can support a broad range of use cases. And I'm just using it in sort of an engineering sense of the word, but I'll say what I mean by that. So it's built using sort of well-established techniques from ML. So if you've been in the machine learning area for a while, you know about transfer learning, and you know about supervised and unsupervised learning. Self-supervised learning is sort of a way, when you have a lot of unsupervised data, to turn it into supervised data, supervised learning, because getting labels is oftentimes hard. So a canonical, a standard example of that is, next word prediction. I have a long text and I want to predict the next word. So I have a long sequence of text. It's just text. There's no labels. But I take 10 words and I try and predict the next word, the 11th word. And so I turn that into a supervised learning problem. Neural networks, you can have non-neural networks, but neural networks. So these are built using things that are known. But you combine them in a certain way, and I think the claim is that it's a new paradigm to do learning and machine learning. And so it's a new paradigm in that sense. The general purpose models, and I'll give an example, that are in some sense reusable infrastructure. That's the goal. That's why they're a foundation. They're not bespoke one-off solutions. So usually, the usual story is I get some data together, I train a classifier, it's a Gaussian process, it's a decision tree, it's a neural network, it's whatever, and it works on this data. That's a bespoke one-off solution. If I get new data, I can't take this model. I got to retrain, or I got to recross validate. I got to redo everything. These are more general purpose. Building them is intensive. Adapting them is not. So the way to think about this is the reason it's a foundation. So Stanford has the term was coined in a Stanford report, and there's a lot of people who use the word foundation model. And I think about 99% of them have not looked at the Stanford report. So I'd suggest if you're going to use the term and think about these things, take a look at the Stanford report. So it's 200 pages long. So I don't have any illusion that you're going to read the whole thing, but read the intro, skim the intro if you're going to be serious about this, because it lays out a certain chain of reasoning. The title is on the opportunities and risks of foundation models. There's opportunities, there's risks, there's good things, there's bad things. If you have a technology, you can use it for good or for evil. But it lays out the justification for calling it that term. But they spend 200 pages to make one point, and the one point is a foundation model is a foundation. It's a foundation on which you build things. It's reusable infrastructure instead of bespoke one-off solutions, right? It's like a road. You put down a road, it can be made out of dirt, it can be made out of blacktop, it can be made out of concrete, it can be made out of lots of things. Depending on what it's made out of and how many lanes it is, it can support different use cases. But once you put it down, people can use it for lots of different things. So it's reusable infrastructure, and then they can build ecosystems around it, right? If you put two roads together, why don't you put a store at the corner, right? So when you build this foundation, you can build other products around it. That's what a lot of companies are doing. Building it's extremely expensive. Building foundation models is resource intensive. $100 million to $1 billion in people, data, compute. You read about how expensive these things are, and all the companies are making big investments because they want to own the space. Adapting them to a specific use case is much less expensive. It can be as cheap as doing in-context learning if you're using language models. But I might have a model and I might want to fine-tune it to a medical corpus or a legal corpus or something. And so I want, a scientific corpus. I want to take it and adapt it to a particular use case. So building the road's expensive, but building a little, a small little road off the road and putting your house at the end of that small road is much less expensive, and you get a lot more traffic because you're building it off the main road. So it's a foundation on which people build things. Okay, so other names that Stanford people considered that they did not use were large language model. That's too specific. The foundation could be not language. It could be vision and images. It could be something scientific and engineering. It could be spatiotemporal. I might build out a spatiotemporal model from simulations or computations or something of the Earth and climate and weather. And once I have that, the question is, what would someone do, right? If you have embeddings that are good for 2 and 3 dimensions in spatiotemporal processes, could I use it for something totally different? Could I use it for things that are marketable? You might be able to come up with something that's marketable, and given those embeddings, could I use it for something that's not marketable, but for scientific? We had a project where we're trying to look for habitable exoplanets. I mean, so you could get embeddings from 2 and 3 dimensions, and question, can you use that to understand, to find habitable exoplanets and other solar systems? That's not immediately marketable, but it's an interesting scientific question. Self-supervised model, that's not so interesting. That's like saying, what's really a road about a road? Oh, it's the particular blacktop mixture. It's too specific. It focuses on some weed level detail. Pre-trained model, that suggests the important action. That's again a weed level thing. Foundational model, this suggests the model provides foundational principles. And this, in a sense, gets to the heart of what we want to talk about for scientific methods, because science wants to find fundamental equations of the universe and fundamental principles of fluid flow and protein structure and whatever. But they didn't go with that term because this is a model. Neural networks are function learners. It's not a claim about the mechanism that the function uses. It's just an input-output mapping. That's core to the structure of computer science theory. That these are functional transformations that don't make claims about the internal mechanisms. That's good and bad, right? That means you can come up with good quality predictors, but it's not robust to making minor changes because the mechanism might be different than your intuition. So the claim is not that I found fundamental principles. The claim is I built a foundation. I could build it out of A or B or C. I could build it out of dirt or concrete or blacktop. But I have a foundation. I haven't made some deep claim about fundamental principles. All right. So the foundation model is designed to emphasize the intended function. It's a foundation rather than the architecture and implementation, these sort of details. Early examples are language models. More recently, there's this stuff with vision and images. And now there's a huge range of things that people are calling foundation models that aren't quite what I just described, but are sort of trying to move in that direction. A big pre-trained model that you might then apply to a different area. And so I think none of these are at best, very few of these areas really have something that is a full foundation in the sense I described, but they're trying to move in that direction. And so what I want to talk about is this even possible in science, and sort of what might need to be done differently in terms of foundational principles. And if you're a scientist thinking about this, it opens lots of scientific questions. And if you're thinking more from an industrial side or something, the question is what's not in current things that you might need in terms of cooking in spatiotemporal or other biases like this, right? So if there's any questions on the chat, Bruce, you're glad to interrupt, but I'll keep marching on unless you interrupt. All right, so that's sort of what I mean by the term foundation model. So can you hope to train a foundation model for scientific ML? So let's talk about that. I think the key thing here is, if we want to think about what does it mean to get a foundation model for scientific machine learning, how to view scientific machine learning. Because back here, the last line here, I said there's lots of things that purport to be foundation models in science: astronomy, radiology, climate, genomics. And most of them say I'm a foundation model for X, where X is not all of science, but chemistry, or X is inorganic chemistry, or X is inorganic chemistry with high oxidation state reactions. And by the time you get very, very fine, it's hard to imagine this is a foundation for anything except the one project you're doing. It's a bespoke solution. So the question is, can you be very broad? Most of these things are not. They're a domain in science, and the model purports to be a foundation for that. And ask how is that? Language models don't take text from one domain; they take text from everything. So is that the right MO to try and develop a foundation model? So this is how I think you should think about scientific machine learning, more ML more generally, but in particular. So this is a slide I stole from some business school class that has nothing to do with machine learning. I searched on horizontal versus vertical business markets. So if you're familiar with business, dynamics or companies or whatever, anything, startups, there's a notion of horizontals and verticals, right? And so this is an important distinction, because if you're a company in a horizontal market and you think you're in a vertical, or vice versa, you'll probably make the wrong decisions. You need to know what playground you're working in, what market you're working in. So vertical integration occurs when the company owns sort of, if you want to call it, different sort of parts of the supply chain. You might produce the commodity, might supply it, might manufacture it, you might distribute it and then sell it, right? You own the whole pipeline. Horizontal integration occurs when you consolidate at a given point of the supply chain. You might supply everything. You might manufacture everything. You might be a distributor for everything. And so you can be a horizontal and sort of a platform, or something that everyone has to go through, or you might be a vertical and you own one narrow thing, but all of it. So chemistry is a vertical. If you're a chemist, you generate the data, you have the theory, you do this, you do that, you get the experiments, the whole pipeline. Biology is a vertical. Physics is a vertical. Electrical engineering is a vertical. Civil engineering is a vertical. Most scientific and engineering areas just historically are vertical, right? Universities hire in verticals. They hire in departments, right? Machine learning is a horizontal. Computer science, builds out horizontals. The point is that the reason the CS theory is framed independent of data is it makes it easy to be a horizontal. So databases, you can put anything in the database, right? And so this is an important distinction because computer science is a thing. It's a clean theory. It may be abstracted from the data. That the claim is it applies to anything. And then, of course, in some applications, it's more or less easy to apply that theory. Computational science is very different. It's not nearly as coherent. It's computational X, computational Y, computational Z. But people that do computational physics have more in common with computational biologists than they do with experimental physicists in many ways, methodologically and what they know. And so most of these scientific areas are verticals. Machine learning is a horizontal. And so foundation models really get at this distinction that they want to build out a horizontal. And so you can't have something too narrow in a given vertical. So machine learning is a horizontal. It provides a standard applicable across multiple areas. So in that sense, it's like the iPhone or roads and railroads. It's like high performance computing or energy infrastructure. It's a horizontal. And domain sciences are verticals. They all need acquisition, the insight, the analysis, and the interpretation. And you have to be a part of our tribe and our domain to push state of the art. So question, where have the high profile successes of scientific machine learning taken place? Right, the Nobel Prize was given out last year. There's been a bunch of other things. They've not taken place in Shell Oil and in Genentech and companies that are scientific or engineering companies as opposed to software companies. The horizontal companies, Google, for example, are the ones that build out this horizontal infrastructure. Then, for whatever reason, or in scientific area A or B or C, it put some resources into it. NVIDIA did it with climate, and so there's a bunch of things. So these successes have taken place in horizontal companies that build out infrastructure and then apply a little bit of science. Not in vertical companies that start with the science as a constraint and then try and sprinkle a little bit of ML on that. That's not been the success for the big one. And think of that like the bitter lesson, right? You want to build out something that's broadly applicable and then put a little bit of science here and there, as opposed to the other way around. Start with my science and then put in just enough ML, but don't overinvest. And so if you're really serious about doing this, this is a key thing, whether you're doing it on the academic research side or thinking about it in terms of a company, right? If you want to live in this vertical, and you may need to justify it because you're going to sell stuff in this vertical, but 99 times out of 100, I see people optimizing too narrowly in that vertical and saying, well, I'm just going to apply ML here because this thing's slightly outside my vertical. And that's like the bitter lesson. It's always a path to not doing something very broadly, I think. So the big successes have taken place in horizontal companies, not vertical companies. And the last bullet's there just to say, a lot of scientists I talk to say, well, we care about the science in our vertical and not other things. And the answer is basically, how many CEOs care about machine learning, right? They don't care about it. They care about revenue and bottom line and stuff, but they see this as an enabling tool. They see this as a powerful horizontal, so they invest in that. And the winners are the ones who invest most heavily in that. So even if you don't care about the other verticals, invest in the horizontal more broadly because you'll win more broadly in your vertical than other ones, just because you've built out that infrastructure. All right. So let's say that you had a meaningfully scientific foundation model, and I'll give some examples of what that might mean, but what could you do on that, or what would that look like? So here's an example, and so this doesn't exist, but this is an example just to focus attention. Let's say that I take data from a couple scientific areas that, there's a fair amount of science out there, fair amount of data. So it could be atmospheric data, right? Climate and weather processes. There's lots of measurements. There's even more simulations. A lot of people do lots and lots of simulations. So numerical weather prediction is better now than it was 70 years ago because people have a lot of high profile, a lot of expensive computation that they've done there. There's been a few high profile successes of ML that are suggestive that this would work more broadly. But even they sit on top of the data generated there. So climate and weather, land, models of water and ecosystem processes. The ground under you is not a nice solid object. It's a complicated object with different densities of materials moving around, and this is true even if you're not at an earthquake zone, right? The subsurface is a very complicated thing, heterogeneous flows, the seismicity. People spend a lot of time simulating this. The differential equations are totally different than the atmosphere, of course, right? So say that you had data, and say that I have data that this could be the atmosphere as a three-dimensional thing. It could also be just of a two-dimensional thing, or the land of a two-dimensional thing. But now if I have information on the flow fields for something on the surface or subsurface, where the subsurface talks to the atmosphere, I have a two-dimensional image of the Earth, right? For all I care, I'm a machine learner. I don't know anything about the domain, right? That's the point of being a horizontal. These images could be satellite images. The satellites look up for exoplanets. They look down, and I might see satellite imagery of the Earth and the hyperspectral imagery. Now I can maybe resolve whether these trees are more healthy than those because they support more water and the underlying groundwater has. So these things don't need to be simulation. They could be just satellite imagery, satellites looking down. So think of a broad range of modalities where the Earth in various ways is measured, and say that you train on data like that, and then I want to do transfer learning, right? I want to do a small, and so now I have a big model that's some infrastructure. Can I do transfer learning to astronomy to discover habitable exoplanets? I gave you this example. This is cute because it's very hard to measure these things. There's a whole bunch of selection biases, and I got involved. I was giving a earlier version of this talk a couple of years ago, and someone came up to me and said, this is sort of remarkable. Can you talk to these other people because they're running machine learning pipelines, and for the relevant physical parameters, they run pipeline A, and they get a number, which is 73 plus or minus 4. And you run a different pipeline, you get 17 plus or minus 8. So totally incomparable intervals. So everything depended on the details of the machine learning pipeline that they had no control over. And so it turns out for exoplanets, it's complicated magnetohydrodynamics on the early solar system, plane. But conditioned on that, that certain future states are possible, and conditioned on that, that there's a certain likelihood that planets will be in the Goldilocks zone, and conditioned on that, certain other things, and so you can measure Jupiter-sized planets going around their suns, at a frequency, several times in an Earth year, so you can get good statistics. So there's a big, long, complicated pipeline. But the embeddings, it may very well be possible, right? Material science, can I learn physics across scales in an end-to-end way? One of the challenges in a lot of materials applications, they even have entire fields and journals called multi-scale modeling. But really, it's taking something at domain is level 1, quantum mechanics. Then I do an all-atom simulation of something. Then I do a continuum. But pasting these different sort of resolutions together is very clunky. This is what ML does well. Can I paste this together in an end-to-end way? Which is related to the subsurface comment up above about the subsurface measurements. Chemistry, can I learn interatomic potentials, right? A lot of work there is done by using Gaussians, and it's this size and the size scale of an atom. If I could learn spatiotemporal embeddings that are richer in some sense, maybe I can get a better representation to say this part of the molecule has a little bit of mass here, and so I could do transfer learning and come up with a novel material. Someone was asking me that the other day in a very particular context. And I said, the answer is not obviously yes. There's some question marks. I can't guarantee it. But it seems very plausible to me that the answer to that's yes. And it seems to me the main barrier in that's just a social one. And a lot of these questions, field A does things differently than field B, and it makes it hard to engineer that collaboration. But it seems to me that technically it's very, very doable. Fire and floods, right? So just as a very U.S. market capital version of a solution to a problem that maybe is better solved in other ways. But so in the U.S., there exists insurance markets for car insurance, right? You own a car, you drive around, you need to have insurance. And the reason basically is that 30,000 people a year, plus or minus something small, die in car accidents. It's very easy to insure that, in terms of death rates. There don't exist markets for insurance for floods or fires and earthquakes. So if you live in California, you're uninsured in some sense. And so as a technical matter, and that's because there's a heavy tail on these events. So question, could I predict tail events to know whether this is a once in a 10-year or once in a 20-year or once in a 100-year event? So that's a very hard thing because you don't have Gaussian concentration. You have these heavy tails, it's these swan events. Can I take embeddings from ML models that might have neural scaling, might have heavy tails, cooked into them, and can I then do fine tuning on a little bit of flood or earthquake or other data like this in order to learn tail events better? And so again, I suspect the answer to that's yes, right? So you could learn well enough to know if it's a once in a 10 or 20 year. And so could you learn that well enough to create a market around that someone's willing to put dollars down and they could create a market around that? Nuclear physics, there's a lot of data that is public. There's a lot of data that's not, and governments want to keep that secret. So question, how ignorant can I be about nuclear physics in order to do something useful there? So what you need to know is that some nuclei have z equals 1 protons, and some have z equals 2 and z equals 3 up to uranium, which has z equals 92. So can I train on public, take my foundation model that I trained on earthquakes and subsurface and language or whatever, and can I do transfer learning to a small amount of nuclear physics data at z equals 1? And z equals 2, and z equals 3, and z equals, and how far up that ladder do I need to march before I learn classified data? Before I learn information at high nuclear zones for fission or fusion that governments have classified. I was on a call about 6 months ago and suggested that to someone at a certain lab, and they said, I can't even be on this call if you're mentioning this, because I guess this was something they were thinking about, or this was less than hypothetical for them, let's say. So you might say, how are these things even possible? Most scientists say my data is specially unique. I generate material science data. It has nothing to do with flood data. It has nothing to do with physics data. It has nothing to do with materials or astronomy data or subsurface. And I mean, I think the lesson in a lot of this is, no, you're not so special, right? Netflix can predict what movies you're going to watch better than you can. And machine learning, is basically the enabler there. And so most domains say you need to get into my domain and become an expert to do something here. And I think the lesson is no. I mean, these methods can cut across domains and be a foundation. So I think this is what might be possible. All right. So let me now switch from what might be possible from a meaningfully scientific model and ask, how might you achieve this? And I want to focus more on the third option, but I want to go through two options because I think actually all three are interesting. So the first option, I made this slide about 2 years ago when language models were a lot less mature. And scientists typically poo-pooed ChatGPT because it would hallucinate and come up with lots of crazy stuff. And so basically just ask ChatGPT or whatever language model you have. Maybe you do some fine-tuning to improve it a little bit, to hypothesize the next scientific discovery, right? Tell me where the top quark is, or tell me how to discover a new protein or something. And if you think about it, actually, that's not so ridiculous. You can put in mathematical reasoning, you can put in anti-hallucination, you can these things are far from perfect, but they're only getting better with time. So that's not actually such a ridiculous option. I mean, if these models can ingest broad swaths of data, I mean, the AI generated stuff on search engines you've probably seen is oftentimes better than the first top 10 links, right? So you can easily imagine iterating with this process and coming up with something meaningful, right? That was a straw man a couple of years ago, but I think it's a very realistic option put into the appropriate pipelines. So interact with that way and fine tune an existing language model to scientific data and figure out to do something smart in context. And can you make that sort of usable as a practical matter much more broadly? So that's one possibility. A second possibility is option 2, actually. And I'm saying ChatGPT, I mean, it could be some other language model, but take the embeddings from a language model, strip out the last layer proverbially, and use it for some other objective. So we actually had an example with this. This was with people at Amazon, and it goes back to this temporal question. So machine learning does well when there's leaderboards, there's tables and numbers for people to compare against, right? And so you can, well, it's the case that there's not so much time series data out there, less than images and language. And the time series data that's out there's not so high quality, I think, from the perspective of training machine learning algorithms. So a lot of it's scientific, but you need to, even if it's de jure public, it's not de facto public, it's hard to access. You need to be a scientific expert in some domain to get it and know about the pre-processing and stuff. So it's hard to use, hard to access, or it's valuable. finance or supply chain companies, whatever, have a lot of data, but they don't want to release it because it's valuable. So the point is there tends not to be a lot of high bar metrics for time series in public data. So the point is, this is with some people at Amazon, and theirs in supply chain, predicting customer demand and so on. So you can imagine that they have high bar internal metrics. And so this is a paper we put up about 6 months, maybe a year ago. Take a language model trained on Wikipedia articles. This was done 2 years ago, and so the language models were much less mature, and we had to use a public one, not the state of the art then. So it was a B- language model 2 years ago. Strip out the last layer, and then take the embeddings, and then use the embeddings for predicting demand for 100 million products. Now the embeddings don't know time, day, week, second, or whatever. So you need to, and they're discrete in tokens and so on. So you got to learn a mapping, but think of it as like, learning the mean and the variance, learning the units. So learn a mapping between these embeddings and the time series. So a 1-layer MLP. And if you want second order information, it's a 2-layer MLP with a nonlinearity. So learn that mapping, and with a very modest effort, you can be sort of comparable to state-of-the-art internal metrics. So what do the Wikipedia articles on which this language model was trained have to do with the demand for dog food and 100 million other products 104 weeks from now? All right, so that's sort of remarkable, actually. So you take the embeddings here trained for this, and they're Wikipedia articles, and it's useful for predicting demand for tennis shoes and shoelaces and dog food and so on 104 weeks from now. So the conjecture is that, well, I mean, it's really learning embeddings that, because time's a very structured metric space, learn heavy-tailed autocorrelations. You're not learning an autoregressive 10 process, and you're not learning a mean field model. You're learning something in between that's capturing the heavy tail structure. And when you do that properly in language and then learn that mapping to the time series, you can extract that from the time series. And so that's probably true much more generally. So that's a real option also. So that's not the option that I want to spend the last 15 minutes on, but I thought I'd mention that. And so the third option I want to talk about here that is why I spent the time early on talking about what a foundation model and how it was trained, is understand, let's call it, the methodology of machine learning. And by that, I mean, how are these things actually trained? And then apply that methodology to scientific data. That data could be text, but for a moment just ignore that, because there's other moving parts here, but it could be. But it could also be simulation. It could be experiments. It could be observation. It could be a lot of different things. And incorporate spatiotemporal inductive biases into the architecture and compute. Do it in a way compatible with the bit or lesson, right? Don't over-optimize, but do it in a way. It might have to be a little bit finer than just a vanilla transformer or a vanilla convolution, but not a lot. I mean, so in a minimalist way, and develop that foundations for scientific ML. All right. So this is something that we had a few years ago. Sort of the question is this insane or does it make sense at all? So there's a scaling question, and I have as I said, slides to the latter half. So I'm going to talk about that a little bit less here and talk about the transfer learning question. So this is sort of a toy version of a problem. So it's a separate question about how to scale stuff up. Let's black box that for a minute. So the basic MO here is you want to scale model and data and compute so none of them saturate, and then transfer learn. And that's not the way people usually do things, right? The way people usually do things is take a data set and run the computation forever till you get tired, right? That's what people do in scientific computing. That's the way people in HPC measure strong and weak scaling. That's really not what you want to do. What you want to do is to take a limit where two things vary. And so this has got attention in neural scaling laws, but if you're capturing heavy-tailed autocorrelations like we did with heavy-tailed self-regularization theory, or other such metrics that capture correlations across scales, you want to capture correlations so as two parameters, or three, but sometimes two are coupled: data size, model size, and compute scale. And you don't want to saturate any of them, because if you saturate any of them, it's like the bit or less, and you're over-optimizing to this amount of data. But if you don't saturate them, you're going to be forward compatible with more data, more compute. So on the left, let's create and pre-train a diverse set of PDE systems. And we're not solving a boutique one for this or that or that, but we're trying to come up with something much broader based. And this is a toy version of that. And then on the right, you want to get sort of a basically a foundation model where you have a whole bunch of types of inputs and use it as a foundation, and then you can transfer, you learn a little bit analogously to Chat GPT. And so what we did here in a very toy case is to say, look at a bunch of different systems, and they each have a parameter, that can go from small to large, let's say. So increasing the diffusion, which happens in certain PDs, increasing the advection diffusion ratio, which happens in other systems, increasing a Helmholtz wave number, it happens in other systems. So how much do I need to know about the domain, and how ignorant can I be? If you know a lot about physics, you know the difference between diffusion and advection and so on. If you don't, it's a niceness parameter. It goes from easy to hard, right? You can easily look at these figures and say, usually on the left, something's a little bit coarser. On the right, you're getting some finer scale information. So it's a little analogous to low to high frequency wave numbers, but it's more fine grained than that because it really depends on the system. And then, on the left, you can see increasing sparsity of Gaussians. It's another knob to go from nice to not nice. So do it for a whole bunch of things, try and get a pretty broad model trained on a pretty broad range of things. So then the question we asked was, could you do that and then port out of distribution, transfer learning? Does it even make sense? So let's say I train on a bunch of systems and the parameters are from 1 to 5 that I trained on. I want to predict when the parameter is 6 or 8 or 10 or 12 or 15. And by now I think people say, yeah, maybe you can obviously do it because they read about some of the remarkable things that ML does. 4 or 5 years ago when we were first starting this, I think people thought the answer would be no. That you train on 1 to 5, it's going to fail on 10. Which, maybe it'll fail on 10, but even if you have a system where the parameter is 10, it's still sitting in 2 or 3 spatial dimensions, and it still has other properties that the 1 to 5 had. So you'd hope you do better than nothing, right? So these plots will show that, and I want to describe what these plots are. So look at the top left. So the question is, I take, this is a very baby foundation model with 32,000 points, right? So I want to train on 32,000 points drawn from this diverse range of PDEs. And then what I want to do is to say, how well do I do if I take 1, 2, 4, 8, 16 points from a new domain, a new value of the physical parameter? How well do I do? How well do I do in 2 cases? One, when I take the existing pre-trained model and fine-tune it with 4 or 8 or 16 points. One, if I train from scratch. And so understand the baseline. I pre-train a model and I give it to you. And then you have 4 or 8 or 16 or 32 points, and you fine-tune this thing or you train from scratch. Now, an immediate criticism is, oh, that's not a fair comparison because this model's seen all 32,000. Right? Well, not all 32,000, 32,000 other points. And the answer, the response is, no, it is a fair comparison. Right? Someone built the road. You didn't pay for the road. You're walking on that road because someone else built it, right? It's a sunk cost. It exists. It's a foundation. So if I train this and give it to you, you can use it for free. So the question is, should I take my 8 points, my 4, 8, 16 points, and fine-tune this thing that's a foundation out there to use, or should I train from scratch? And so what you see here is that. So really, in that sense, it's a fair comparison because this is a sunk cost. And so what you see on the top left is that the solid line, so here, the pre-training is 1 to 5, and the downstream testing, the parameter is 1 to 2.5. So really, it's in domain. But, and what you see is that if I have 32,000 points and I fine-tune to 2 or 3 more that are secretly in domain, I get the solid line. So my quality metric of error is 10 to the minus 3 or so. And it doesn't change as I get more and more points because I've saturated the system. Because I have not satisfied anything analogous to neural scaling. I've saturated. I'm just giving you more data points that are in domain. And so if I have 1 or 2 or 4 or 8 or 16 points and I train from scratch, I do not so well, 10 to the 0. But as this increases to 32,000, I do better. And they end up touching each other because, I trained with 32,000 points in domain. Right, so that's a sanity check. So now what if you train on 1 to 5 and test on, I can't see the numbers, but 2 to 7. So they overlap a little bit. And the answer is that the baseline model does a little bit worse, not a lot. Training from scratch starts out bad, but then ends up getting better. And actually, that's probably noise, but does better sort of in a relatively stable way. If now I train on 1 to 5 and test on 5 to 10, The baseline's a little bit worse, as you'd expect, right? Because now the fine tuning is to data that's out of domain. Training from scratch still does order of magnitude and a half worse, and they both get down and touch each other at 32,000. If now I train on 1 to 5 and test on 10 to 20, so clearly I'm out of domain, do a little bit worse still, right? The solid line's worse, but now with a bit of fine tuning, it does better. If I train from scratch, it's an order of magnitude worse, but still parallels the line. So the fact that those two things parallel each other and don't touch at 32,000 suggests you're not in the saturated regime, right? You're something more analogous to what you'd see with neural scaling laws. We have two parameters that are tracking each other, but one doesn't saturate. So this is interesting, and so these results suggest that, I mean, the paper has, a dozen or 2 dozen plots in the main paper and appendix. So this is just one example to try and justify the claim, but the short answer is yes. Train on this, transfer learning to something out of domain, you do non-trivially better, even in a toy situation, certainly in something much, much bigger. So we see that. I could show you lots of other plots, but in the interest of time, I won't. But just to say, so the idea of transfer learning like that with spatiotemporal data, it'll work. Others have followed up and got substantially the same sort of results. Okay, so does incorporating physical knowledge help, and if so, how? The short answer is it can, but you can easily do it wrong. So a couple of years ago, there was a lot of interest in something called PINNs, P-I-N-N-S, physics-informed neural networks. And they basically just tack on some physics information as a regularizer. Sort of makes intuitive sense. Question, how does it perform? The answer is they were very finicky and hard to get to work. There's just lots of knobs, so you can always find a success. The first paper in a machine learning venue was this one we had, and the title was just characterizing failure modes of physics-informed neural networks. And there's just lots of failure modes. They work in nice cases, and then they just break. And there's a range of ways to fix that break, and most good engineers would think about it and come up with them. But the fixes are orthogonal to machine learning methodology. They really don't map to the methodology of machine learning that we've been talking about. And so we had this result, and 6 months later, CACM put up sort of a summary article. And I came to find out that sometimes the title of the article is written by an editor, and the article is written by someone else. And so the title here is Neural Networks Learn to Speed Up Simulation. So it's sort of a positive title because people want to read articles with positive titles. The subtitle is the interesting thing. Physics-informed machine learning is gaining attention, but it suffers from training issues. And issues is a euphemism there, right? It breaks and has a lot of problems, precisely because these models have a lot of failure modes. So the answer is incorporating the physics can help, but it can also make things a lot worse. All right. So if you want to build out foundations, and let me just wrap up. So we've done a bunch of work, sort of motivated by these general questions, and trying to characterize some of those failure modes. And so, for example, you might say superbench is a super resolution benchmark. If you train to data that is continuous, does the machine learning model know that and see that or not? And the answer is it doesn't. There's nothing in the structure of the machine learning models that sees that. So you got to cook that in. And even things that neural ODEs or neural operators that structurally, in principle, could incorporate that don't. And so they don't have this super resolution property. Traditional versus modern uncertainty quantification. The usual intuition is that there's a trade-off in terms of bias and variance. As I have a hyperparameter and I cross-validate and I choose the best value because bias and variance operate in different ways. If you're dealing with models that interpolate, which is a lot of models do, there's this phenomena where when you interpolate, the bias and variance can behave in different ways, and so that trade-off is very different. You see that with point predictions, and you see that with uncertainty quantification. That's particularly of interest in a lot of scientific applications. You can ask can I use ideas from numerical analysis, because numerical analysis is an interesting area that frames questions in a way that are well posed and says I'm not going to ask the question otherwise. And so there's a lot of work there on sort of mapping discrete and continuous, and it goes by the name numerical convergence test. So can I apply those ideas to say I have a machine learning model and that has certain good stability properties with respect to continuous space and time? And so the short answer is yes, and I think there's a lot of foundational questions there. Prob conserve, say that I want to incorporate hard constraints. How can I do that? Exactly addressing the failure mode that the PINNs have. And the answer is you can do that, but you got to wrap it up in an oblique projection and try to change that in a differentiable end-to-end way. And so a whole bunch of foundational questions there on how to do that properly. If you're familiar with statistics and regression diagnostics, you'd fit your regression algorithm, and if the residual errors look like this, look like a U-shaped, you say, geez, I'm missing a feature that's quadratic. Put the quadratic in, and now my residual errors are less and flat. Can you come up with regression diagnostics like that for models that interpolate? So the way to do that would be to look at the weight matrices of trained neural networks. And the weight matrices, everything before 2013, the inflection point with ImageNet, had what statisticians would call a bulk plus spike property, a bunch of random stuff and some eigenvalues sticking out. Everything post 2013 has heavy-tailed eigenvalues. And so that has very significant implications for doing diagnostics and for characterizing properties of training and inference. Time series, I gave you a couple examples of that, how to incorporate time as a first-class citizen in machine learning models. And one way to do that is this neural discrete equilibrium, which basically takes hard time series, hard differential equations, and does a lifting of kinetic theory to say this is the right way to incorporate conservation laws. Along the lines of the bitter lesson, here's a structure. I want to incorporate a physical constraint, and doing that in a very, very weak way that has parameters that play well with the machine learning methodology. So a whole bunch of methods there. And, as I said, this slide deck is on the web page, so you can go through any of these. There's a bunch of implementations. A lot of this stuff depends on latency bandwidth trade-offs, and so we've looked at a bunch of things like this. You can use randomized matrix algorithms. They have better communication profiles. You can do quantization and other things that typically at training or inference, typically at inference, but you can also ask about training. Applications, there's a lot of, I gave you sort of an example of some of the motivating applications. We've done a bunch of things on earthquakes and a range of other things. We actually have a project where we're trying to build this out and sort of address I think the main technical challenges of this lack of neural scaling. You want to scale model and data and compute so none of them saturate, but having control on what machine learners would call out of distribution, but it's oftentimes very structured out of distribution, subgrid resolution or something having to do with the physical constraint that satisfies some general, some other sort of principle. And then the way you'd incorporate different modalities is sometimes different. I mean, you can steal a lot of ideas from the general ML, and then sometimes there's stuff that's a little bit different. So looking forward, hopefully, if you learn nothing else, foundation models are infrastructure. It's a foundation on which you build stuff. If you really don't want to read the 200-page Stanford report or the 20-page intro, there's one word to say what these things are. They're foundation. And then it's the foundation on which you build stuff. So like the computer, iPhone, or bridges, or an electrical grid, right? They're impressive and they work until they break. And if you want to understand sort of how to build out something for mission-critical applications that involve spatiotemporal or scientific or engineering, I think some of the things I've been talking about are relevant. And I think to understand why they work, you would just take a look at history, right? Computer science versus computational science. And they've bifurcated in they've evolved and bifurcated in very different ways at universities, similarly industries. I think you'll see a similar sort of thing here in terms of forcing functions. And, are you computing at very low, or do you compute with different levels of abstraction? Similar questions will arise. So the general question here then hopefully piqued some people's interest is, if you're interested in foundational questions, this is great, because I think there's a lot of foundational questions we've tapped into here on how to give a strong, robust foundations for scientific machine learning. If you don't care about foundational questions and you want to do something in scientific machine learning, hopefully it's also piqued your interest a little bit to say, you got to think about this thing a little bit more broadly rather than narrowly. There's a complicated trade-off in terms of horizontals and verticals and interdisciplinary stuff. And thinking this through is something that I think a lot of people are doing, and a real challenge, but I think sort of well worth it. All right, so I think I'm at the hour, and I think we had an hour plus not 30 minutes. So let me pause. I'm glad I can go into any more detail on any of these things, or people had other sorts of questions. Glad to go into that, or anything you want.
Okay, sure. So let's just open up the floor for questions from the audience. Thank you so much for the amazing talk, Professor. And as the same, we will give away 10 open-routed API keys to the audience today. So feel free to drop your questions in the live chat. Let's see. So the first question we have here is, What are the main challenges in building a science-based model?
What are the main challenges? I think so. I took the easy route today, and I talked about foundational methods.
Mhm.
There's a whole bunch of technical challenges, and the technical challenges are, correlated with what I talked about. They're correlated with, this slide. There's a whole bunch of things at the spatiotemporal. I think the main challenges are not the technical. They're really, for lack of a better term, cultural or sociological or something. Most scientists want to do science in their one narrow domain vertical. And so they don't want to know ML more broadly. And most ML people want to build out broad infrastructure, and the domain is just an excuse to apply their methods. And if you're building out the horizontal infrastructure and you're looking for a domain to apply methods, you'll look at the domain that's easiest to apply the methods to. Vision, advertising, language, whatever, not high energy physics, right? And so the question is, how do you integrate this vertical and horizontal? So computer science is born of numerical analysis, right? I mean, PDEs and numerical simulations. But doing the computation in a given vertical was very difficult, and formulating a general theory was very difficult. And so really was banished from computer science. And so that's why computational science has different verticals. And computer science theory sits on Turing machines and other stuff. And then that had very particular consequences as the areas evolved with computer science versus computational science, area A or B or C. So I actually think the biggest challenge in terms of building out a broad-based scientific foundation model that'll cut across domains is those sort of, for lack of a better term, cultural issues or sociological issues between areas, right? I think it's particularly challenging in the US given the funding structure and stuff. I mean, it's one of these things, it's hard to get a very new technology when there exists a lot of existing stakeholders that sort of fear that it's going to cannibalize their markets, as it were.
Okay, great. And the next question is, what are the latest research ideas regarding the training stability of LLMs?
The training stability. I mean, I think I think basically there's good, well, theoretical reasons, and if you look at what people in practice do, empirical reasons to say you want the training to be unstable.
Mhm.
And so for example, you see people train something and then it goes unstable. They'll go back to the last checkpoint and fiddle with some random seed or learning rate and run it until it blows up again. They'll go back to the last checkpoint. So in a sense, you want the training. So physics people had this term, and some machine learning people sort of rediscovered it. It's called edge of stability, where you want the dynamics to be almost unstable. And there's sort of a good reason why you might want that. I mean, when we did the Weight Watcher diagnostics, the phenomenology there was that the trained models that you actually look at. So this is stuff with Charles Martin that we did over the years, where we developed a phenomenology, a theory, but a phenomenological theory. We looked at the data and came up with a taxonomy where you can make predictions on model quality looking at eigenvalue structure and use ideas from heavy-tailed random matrix theory. And basically the point of that theory is that you have a data set, and if you see something random and something with a spike, you tell yourself a story. The data's IID up to that low rank factor or whatever, and then you get statistical significance here and say that's the signal. But if the data is really strongly correlated over many scales, which is what you see with neural scaling, which is what you see with the Weight Watcher diagnostics, you can't apply that. And so it really suggests that you have correlations over many scales. And so operating, to extract the information, you want to be heavy-tailed, but as close as possible to the transition point where you lose variance. So I think that's the leading order thing. And so it's a bug or a feature. So there's a lot of little things you can do to improve the stability. You clip gradients or this or that. But I think it's two sides of the same coin, right? That you really want to be working in the regime where it's almost unstable, because that's allowing you to extract correlations over many scales best.
Okay. The third question is, How is the generalizability of scientific machine learning, and how can generalization be achieved through model foundational capabilities and product pathways?
Yeah, I mean, so generalization in machine learning is basically, I think, take the training data, cut it in half, take the data, cut it in half, train, and then evaluate on the other half, and that's a proxy for evaluating on the unseen hypothesized data. And so you build VC theory and whatnot around it. That's not typically what's done with neural networks. There you take all the data and you just train until you get tired. The training error is zero or the perplexity gets small. And so for that, the generalization theory is much weaker. Now, sometimes and often, I mean, the VC stuff led to vacuous results. Using Bayesian ideas, you can get finer bounds. Using statistical mechanics ideas, you can get finer bounds, but those are sort of heavier duty in other ways, and I think the community likes them less. So I think there's a bunch of good questions on what's the right way to structure generalization theory, in particular in a situation like where you have that heavy-tailed mechanistic universality, which the heavy-tailed self-regulation theory is sort of trying to characterize. Because there, in a sense, you can't, the data is correlated and in a much stronger way than traditionally. So I think there's still open theoretical questions there, and that's true for scientific machine learning or not. Now, for scientific, I think ML, I guess more generally also, but in particular scientific ML, people sometimes use the word generalization to mean out of domain generalization, which is not generalization, it's sort of something out of domain, but the word's sometimes used that way.
Mhm.
There, I mean, I think you have all the usual problems you have with general ML, right? How do you characterize out of domain? I mean, I think in a sense, some of the challenges will be a little bit easier because you do have more knowledge. And one of the things you want out of domain is you cut the time step in half. Things shouldn't fall apart. If they fall apart, this was the continuous net thing addressed. If they fall apart, you have something wrong. But you also have a good guiding principle. Why? So if you're doing fluids in a laminar regime, laminar is nice. Something should behave smoothly. If you're doing fluids in a turbulent regime, it's not as nice, but you can characterize something. So there's a lot of subgrid like the superbench. I mean, there's a lot of situations where you can go out of domain, but it should behave in sort of a structured way. I mean, if you have an advective term or you have a conservation principle, you can go out of domain, but that has to be conserved. So I think state-of-the-art models don't really deal with that sufficiently maturely yet. But I think there's things that are nominally out of domain that if you respect those sort of broader physical principles, spatiotemporal continuity, whatever, you could have models that are much more robust, certainly than they currently are. And beyond that, I think there's a lot of methods from. This is one of the places where ideas from computer vision actually do well. Generate lots more data that's adversarial, but is a little bit out of domain, but using the domain data you have as a prior, and that can improve lots of things because you have a lot more data that's a little bit less reliable.
Okay. The next question is, will scientific machine learning eventually become AGI or ASI?
So I don't know what AGI is. I guess it's this term people use, and it's a funny thing because if I ask people what it is, they give me a set of words, but then if I ask what those words mean, they say, well, it's sort of like this, and then if I ask what does sort of like this mean, they don't know.
Hmm.
So I think this gets to what's a forcing, what's acceptable to believe and what's not acceptable to believe, sort of in the area, right? Scientists tend to get inference not by necessarily statistical principles, but by looking at very complicated things in the world and asking a very narrow set of questions. They'll only ask falsifiable questions, namely questions for which they can get a meaningful scientific answer. If I can't, and so whether I'm doing astronomy when I'm doing observational stuff or molecular biology where I can run an experiment or physics or whatever, I try and ask just falsifiable questions. So the usual story is I go look at the world, I form a hypothesis, I run an experiment. Okay, if it's observational, it gets a little more complicated, but I don't ask certain questions. I don't ask questions that I can't get a yes/no answer to. I only ask falsifiable questions. And that's very different than machine learning. And it's also different than engineering, right? Engineering, you just want to build stuff. And if it works, it's good. You declare success, right? So it doesn't need to be sort of right? I could give you code that's, I mean, some areas of engineering, like civil engineering, might sit on top of physics, but at the end of the day, here's a bridge. Software engineering in particular, there's a level of abstraction where it's not sort of real. It's just a product, and here it is. And so if you're doing more of an engineering forcing function, you're not tethered to sort of what's right or true in a falsifiable way. You just want to build something. So I think the forcing function for a lot of ML is to build these intelligent systems where intelligence is undefined, meaning it's not a falsifiable concept. And so, so I don't know, I think that these scientific ML questions can address a bunch of things, and incorporating the domain insight can do some things, but I don't know. I think there's a real disconnect between this term that is sort of poorly defined and doesn't have an operational meaning, and a lot of the scientific use cases where they try and have they only ask a set of questions that can get that answer. And so one of the challenges with tying these two things together is exactly that.
Okay, I think that's pretty much all the questions today. So thank you again, Professor. And thank you to all participants for your insightful questions. We'll share the replay and slides and all the key takeaways on our website. So don't forget to follow us on our socials, join the Discord and Telegram group. Stay tuned for the upcoming episode. So see you next week. Bye.
All right, thank you.